Welcome to this explainer. If you love figuring out exactly how massive, complex projects go from just a tiny spark of an idea to a monumental reality, well, you're in exactly the right place. Today, we're looking at the high-stakes world of naval architecture and ship design. Let's just dive right in.
Picture this. You're sitting in a sleek corporate boardroom. An ambitious ship owner slaps a napkin sketch right onto the table. It's really just a rough outline, a few scribbled numbers. Now, cut to exactly 3 years later. A finished 300-meter steel Leviathan, weighing tens of thousands of tons, slides gracefully into the open ocean. How on earth do you get from that flimsy piece of paper to a floating fortress? Well, it definitely doesn't happen by accident, and it certainly doesn't happen by guessing. It happens through 3 distinct, rigorously controlled stages.
So, here's our roadmap for today. We'll start with the blueprint to reality, then walk through the 3 main stages of design: concept, preliminary, and contract. And finally, we'll wrap up by looking at the true cost of change.
Let's kick things off with Section 1, the blueprint to reality, structuring the impossible.
Because ship design operates in a wildly dynamic environment, having a strict, structured approach isn't just nice to have, it's absolutely essential. The process always proceeds through 3 increasingly rigorous stages: concept, preliminary, and contract design. And the golden rule here? You cannot skip a step. If you rush that initial concept or kind of gloss over the preliminary math, you don't just end up with a slightly imperfect ship. You build the entirely wrong ship. And trust me, that's a mistake that can cost hundreds of millions of dollars.
Which brings us to stage 1, concept design, basically answering the question, is this even feasible?
Now at this point, we aren't doing any precise calculations. You're not going to see engineers sweating over exact steel plate thicknesses just yet. Instead, what we have is a basic techno-economic assessment. The naval architect is working in broad strokes, figuring out rough estimates for the main dimensions, stuff like length overall, beam, draft, and deadweight tonnage, along with a general arrangement sketch. We really just want to see if the owner's dream can actually be translated into a profitable reality.
And you know, those initial demands, they can be incredibly simple. The tangible owner requirements that kick off this entire phase might literally just be, hey, I need a ship that can carry 80,000 tons of iron ore, maintain 14 knots in average weather, and operate for 25 years. That's it. And from those 3 little bullet points, the naval architect has to conjure up a massive vessel. If this concept design proves that the combination is both economically and technically viable, boom, the project gets the green light.
Moving right along to Stage 2, preliminary design. This is where the engineering actually begins.
The very first thing that happens here is the hull form gets developed and completely locked in. We're talking about the precise, mathematical shape of the underwater body mapped out using lines plans with water lines and buttock lines. This is absolutely crucial, because the hull form dictates exactly how that ship is going to move through the water. It has to be designed to offer the absolute minimum resistance possible, so you can hit those 14 knots without burning an absolute fortune in fuel.
And man, the sheer volume of math involved in Stage 2 is staggering, but it directly guarantees the safety and performance of the vessel. For instance, hydrostatics confirms the ship floats at exactly the right draft, not too high, not too low. Stability calculations, those are literally life or death. They prove the ship will right itself in a storm and won't capsize. Then you have powering calculations to determine the exact engine size needed to push 80,000 tons of cargo through the water. And finally, structure. This sketches out the internal skeleton, deciding exactly where the main frames, bulkheads, and decks need to go to hold the whole shebang together.
All right, Stage 3, contract design, the finished article.
At this stage, we are dealing with a mind-boggling scale of detail. Thanks to modern computer-aided design, or CAD, the motto nowadays is basically draw it once, build it directly. The ship is modeled entirely digitally in 3D, yielding midship sections, structural plans, piping schematics, and electrical one-lines. They even run clash detection software to make sure, say, a ventilation duct doesn't accidentally run straight through a main steel beam. It is the complete, finished article, built perfectly in data long before a single spark flies in the physical shipyard.
And this is a big deal, because the contract design isn't just a technical guide. It satisfies the building conditions and acts as the strict legal document between the shipyard and the owner. It defines exactly what will be built. If the owner suddenly gets a new idea and wants to change something at this stage, well, it's going to cost them dearly. A single alteration here isn't just erasing a line, it cascades through hundreds of highly detailed interconnected drawings and digital models.
And that leads us perfectly into Section 5, the cost of change, and exactly why these rigid stages exist in the first place.
You might be wondering, why do naval architects insist on these inflexible stages instead of just kind of figuring it out as they go? Well, look at this comparison. If you make a change early on, during the concept stage, the cost is practically zero. You literally just erase a pencil sketch or toss a sticky note in the trash. But if you make that exact same change late in the game, during construction, you are literally cutting apart and rebuilding heavy welded steel right there on the berth.
The cost of making a change rockets upward exponentially. Let's say a change costs 1 unit of effort or money in the concept stage. That jumps to 15 times the amount in the preliminary stage because engineers have to redo all that complex math we just talked about. And by the build stage, that cost factor explodes to 100. A late modification in the shipyard can easily cost millions of dollars and delay the ship's delivery by months. In the maritime industry, time is money and steel is unforgiving.
So let's do a quick recap. These 3 stages aren't just arbitrary drawing phases, they are critical quality gates, specifically designed to catch mistakes when they are still cheap to fix. Concept asks, is it feasible? Preliminary asks, does the engineering actually work? And contract ensures every single detail is defined before the very first piece of steel is cut. Only by passing through these exact gates can a napkin sketch safely become a profitable reality.
But wait, this leaves us with a massive, fascinating puzzle. We know that in ship design, changing the cargo weight changes the draft, which changes the engine size, which changes the fuel needed, which changes the weight again, right? Everything is connected. So how on earth do naval architects balance all these competing parameters simultaneously without getting stuck in an endless loop of starting over? Well, the answer lies in a legendary framework known as the design spiral. It's one of the most elegant solutions in all of engineering, but how exactly does it converge on the perfect ship? Well, that is a brilliant question to ponder, and exactly what we'll uncover next time. Thank you for joining me on this explainer, and keep learning.